Hello, this is the Ancient and Medieval History Lecture for Wednesday, October 6th, 2021. Today is Crazy Day here at the Charter Academy, and I see a number of people are dressing in jarringly uncoordinated ways. I'll try not to get a headache. I will point out that I am probably the only person in here that has a t-shirt of me. This was made about 14 years ago by colleagues and students. I think it says, what does it say?
Have I
obfuscated
my intentions with my verbiage?
Yes. Have I obfuscated my intentions with my verbiage? Which is the way I speak, and it certainly is the way I spoke 14 years ago. So, in any case, what we have done up until now is we have explored the various myths of people around the world as to why the world is the way it is, which is what creation myths are about. Now, our society, being rather pedantically literal, it has a set of creation myths that most people believe in without understanding the underlying science. So in that sense, it is mythic. Also, these myths of ours in our society, whether you happen to subscribe to them or not, are not about why. They are industrial age myths, which rather than focusing on the interesting question of why, explores the, to me at least, less interesting question of how. We are on the page of notes that reads at the top, our contemporary creation myth, universal history timeline, number 1. And it starts 15 billion years ago. That's 15,000 million years ago. It is near the beginning. It is a horizontal page. It is the first timeline page in the notes. And the first item is unknowable and indescribable. There you go. Okay. So presumably people have gotten to the very first timeline page. One more. There we go. Let me find it. Okay. So it looks like you're all there. Our creation myth is Big Bang, astrophysics, and biological evolution. Now, there are those who argue that the Big Bang is simply the latest iteration in a possible infinite number of Big Bangs and Big Crushes, or Big Bangs and universal dissipation, followed by another rip or breeding of space-time. But that's, at this point, all mythical. Even to scientists, they are working on it at the edge of theory, but nothing has been demonstrated yet. The Big Bang was demonstrated by a background noise in the universe, a persistent radio signal, which seems to be residue from this event. In any event, we're going to take it as real, and I will tell you as I know it. If you have insights or thoughts or other ideas, be welcome to chime in. What was before the Big Bang? What is outside of the universe? Well, most people would instinctively say that emptiness would have been before the Big Bang. That open space filled with nothing, not even dust particles. But that's wrong. It's wrong because what we conceive of as open space is merely a part of the fabric of space-time. It is a part and parcel of our universe. It could have been a universe of cotton candy for all we know before the Big Bang. Outside of the universe, it could still be a universe of cotton candy. We don't have a clue. It is an existential, unknowable what came before our universe. Because every measuring stick that we have, every sense that we have, and every theory that we have is based upon an understanding of our physical universe. And since this applies to something other than that, we don't know. But it's probably not empty space as you or I conceive it. Then, about 14.5 billion years ago, that's 14 billion, that's 1,400 million, 1,400 million, I gotta do this. Okay, 14,500,000,000. So that's 14,500 million years ago. It's a long time. But it's not infinite. Bing! Something appears. We don't know why. God may have said, let there be light, or something was simply ready to be born, or Brahma decided to enter the universal egg. We don't know. What we do know is that the first thing of our universe that intrudes, that appears, is a geometrical point. Now make your geometry teacher proud. What are the characteristics of a geometrical point? What are the characteristics? What do we know, and what do we know geographical point is and is not? Rolling the dice. You all should know this. Math teacher is going to be sad. It's sad, I tells you. I think that's Mrs. Hammond. For most of you, is it? Oh, okay. I don't know Mrs. Snitty as well as I know Mrs. Hammond. I do know Mrs. Hammond gets sad when people don't learn. 19. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19. Describe to me, to the best of your ability, a geometric point.
Singular place on a graph, number line, or any type of coordinate plane.
Okay. So it's a place.
Yeah.
It is a location. Does it have any mass? No. Does it have any area? No. It is, without exception, the smallest discrete thing that we can think of. It is a location in space-time or of space-time without mass, without area, without weight. And that was the first moment of our universe. A location. Actually, unknowable. Boom! The Big Bang. From that geometrical point, which contained the potentiality for everything that is, was, or ever shall be in our universe, our universe explodes into being. Now, in the opening moments of the universe, everything that is within the explosion. Ladies and gentlemen, it still is. Everything that is inside the explosion. The explosion is still going on. 14.5 billion years later, the universe is expanding. What is beyond that expansion? We don't know. What is it expanding into? We don't know. Could be a universe of cotton candy. We don't know. We are within an ongoing explosion. In that sense, the Zoroastrians were right that we live within an ongoing explosion. Who knows? The Big Bang could have been caused by Ahriman and Ormuzd, or by Angra Mainyu and Ahura Mazda coming into contact with one another. They could have been right. Now, in the opening moments, it's what I choose to call the era of solid light. Now, the light coming out of these fluorescent bulbs is registered by your eyes, passed through your optic nerve to your brain, and interpreted as the vision that you see. I do this, and because you all have eyes that work, and optic nerves that are intact, and brains that are designed to process all of that, you can tell I'm waving my fingers. You can tell I'm about to eat the waving fingers, and then because you can see me. Light, to us, is merely the electromagnetic radiation that we are biologically designed to pick up. It is as if our eyes are radios, and the ambient light around us are radio waves, and we are simply tuned into them. Now, we know that the visible spectrum of light that we can see is only but a small part of that electromagnetic spectrum. We know that ultraviolet light exists beyond one end of our visible spectrum of light, and we know that infrared light exists on the other end. Insects have the ability to perceive ultraviolet light. Snakes have the ability to perceive the infrared. So even on our little pedestrian parochial planet Earth, we have evidence that our senses do not discern everything. Quite the contrary, our senses are limited to a certain set of frequencies. It's like having a radio in your car compared to a ham radio. A ham radio can pick up anything. Shortwave, long wave, AM, FM. A normal car radio, oh God, you're not used to car radios because you have computerized stuff, but a normal car radio just has AM and FM. Limited spectrum of the available spectrum or wavelengths that are out there. However, in this opening moment, the entire universe is a white-hot light explosion. What that means is there is no emptiness yet. The entire universe is made of solid light. Imagine light, just light, so heavy that an infinitesimal portion of it would weigh more, mass more, than our entire solar system. All the planets, all the asteroids, all the comets, the sun, all rolled up, tiny infinitesimal of solid light at the beginning of the universe is more significant, more massive. And then, in this era of solid light, an emptier space appears. Now, this is actually similar to the Chinese myth that starts us out with a cosmic chaos. And then an empty spot appears. And from that empty spot appears, other empty spots begin to appear. Now, at first, the universe is entirely solid. But today, the universe is a lot of empty space with matter and energy coursing through it. So the empty proportion of the universe goes up as the solid proportion goes down. It's hard to imagine a universe that's mostly solid light. But eventually, fairly early on actually, the proportion changes and the universe is not mostly solid light. In fact, light begins to diffuse and become more like energy and matter as we understand it today. Solid light is both and neither, energy and matter. So the first difference is the emptier spot. The two motive forces that guide the physical universe, I'm speaking in a Newtonian fashion, gravity and inertia. Imagine that that podium is planet Earth. I am orbiting it as Luna, the moon. So I'm going around it in a fairly predictable course, we hope, in a course that is not going to result in a collision, nor in the moon flying off into space. What is an orbit but a balance between gravity and inertia? The attractive force in nature, or the bend within space-time caused by a supermassive object like the planet, is drawing the moon straight towards the core. Simultaneously, the moon is moving at an incredibly fast speed. And Newton says an object once in motion tends to remain in motion. If it was simply the inertia of the moon would fly off into space in a fairly straight line. But these two forces are balanced. The moon is both flying away from the Earth and falling towards the center of the Earth in a balanced fashion, which produces the curve of the moon's orbit, the ellipse that is the moon's orbit around planet Earth. It is both falling and flying away at the same time, and because those forces are in balance, the Earth is orbited by the moon and has been for most of its existence. What is gravity? Einstein posits a visual mode of imagining what space-time curvature looks like. Imagine that we're all around the outer edge of this classroom. Yes, imagine it. And each of us are holding onto a nice thick cotton sheet. And we're all holding it around the edges, and that cotton sheet is taut and flat, and that is space-time without the impingement of gravity. Then we take a golf ball or a ping pong ball. Let's start with a ping pong ball. Toss it onto the sheet. What's going to happen? Well, the ping pong ball is fairly light, and we're pulling pretty strongly. But inevitably, there'll be a slight dimple in the sheet caused by the ping pong ball. Slight. You get rid of the ping pong ball, put a golf ball on. Bigger dimple. You toss a bowling ball on there, and suddenly we either have a torn sheet or everyone gets yanked inwards towards the center. Because the bowling ball, I'm not talking duck pin bowling, I'm talking real bowling, the kind with the balls that you throw with three fingers. A bowling ball will go to the floor unless we are very careful. The bowling ball is like the sun. A baseball or a softball or a golf ball is like the various planets. Gravity distorts space-time, creating in effect, a de facto attractive force. Inertia is simply the tendency of an object, once in a particular motion, to remain in that motion unless something acts upon it to degrade the motion or to change the course of it. Now, some of you can certainly see already why I don't teach science, but I'm doing the best I can. Now, about 13 billion years ago, I don't remember my own chart. Yeah, about 13 billion years ago, there is this roiling particulate matter that's getting clumpier. Now, every object has a gravity well. If you and I were floating in space in spacesuits, we would tend to come together because you and I do have a tiny little gravity field. And in space, assuming that there is no other gravity field acting on us, we will tend to come together. Objects tend to float. So we've got this cosmic dust, rock, mass, stuff, soup, whatever. Probably not liquid, though. And it's beginning to attract more and more and more and more and more to it. And the clumps are getting heavier and more solid, and heavier and more solid, and heavier and more solid. And as the attraction brings more stuff, the gravity well gets bigger because the mass increases. What happens is, as new matter is brought in, and as the matter is settling out, it tends to cause friction, rubbing, pressing, pressure, heat, pressure, heat, boom! Gravity ignites the dust. The first star is born. Out of this process of the compression of cosmic dust, rocks, debris left over from the Big Bang, and then boom, 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 all around the universe, various clumps begin to appear. Stars predate galaxies and planets. Now, what happens on a macro scale, on a very large scale, is that lots of stars begin to affect and attract one another. So the stars themselves begin to come together, but that's not all. There are also objects in the universe, calling them objects, they're really locations, called hypermass. Another word for a hypermass is a black hole. A black hole is a location with a gravity well so steep that the normal laws of space and time break down. They are a massively attracting force. And what we tend to believe today is that as the stars cohere, they tend to swirl or clump around supermassive hypermasses, supermassive black holes. So the Milky Way galaxy, our galaxy, which we'll talk about in a moment, has a supermassive black hole. Andromeda does, even bigger, about twice as big as ours actually. And the other galaxies tend to form as a result of the mutually attractive force of the stars, gravity, and the attractive force of the black holes. If you want to think of the black holes as holes in the universe, what they do is they suck up matter, including stars. Left alone, without, well, I'll do our galaxy and then we'll talk about it. So the stars tend to organize in large clusters called galaxies, island universes they used to be called. About 10 billion years ago, our Milky Way galaxy forms. It is a lenticular or spiral galaxy. It has several arms. We are located about 2/3 of the way out in the Orion spur of the Sagittarius arm of the Milky Way, and in the center there's this shapely center, this bright zone. Now, why would a black hole look like a bright zone? Because at the edge of a black hole's gravity well is what's called an event horizon. We can perceive everything up to the event horizon. So you've got a probe that we sent, and the probe is going to, and we've never done this, probe the black hole. So beep, 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 and it's moving faster and faster because it's in the gravity well of the black hole. Beep, 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 beep. And eventually it will reach the event horizon, which is a point where even light will not escape from the black hole. Beep, 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 and it's gone. What we believe is that the probe will then be spaghettified. And what that means is, it's not a sacrament of the flying spaghetti monster, the Pastafarian religion, is that the matter will be so distended, so stretched out, that its various component parts will just stretch out of all recognition. And then it's gone. It's gone wherever the black hole puts all of its mass. Whether it's just adds to its height, we don't know. We have no direct evidence because we can't perceive anything, because even light can't escape the event horizon of a black hole. So our galaxy forms 10 billion years ago. Now, we're on the next page. relatively nearby in stellar terms, a star is getting old. Shani, that star is close to consuming all of its atomic fuel, all of its hydrogen. Now, some stars fade away. They slowly wither and slowly wither and slowly wither and slowly wither and slowly. They're gone. They become brown dwarfs, they're just gone. Other stars decide, better to burn out than fade away. And like an incandescent light bulb, just before it goes dark, an incandescent light bulb, not one of these fluorescents, tends to get super bright in its final moments, consuming its remaining ability to transmit light. A nearby star goes nova. That's what it's called. When a star decides that it's time to spend all of its fuel in one last glorious flare, that's a nova. When a really big star does that, that's a supernova. Supernovas are not nearly as heavy as black holes, but they are also massive gravity sources. Now, we imagine that at some point our star, our star Sol, will go nova. And when it does, assuming that it does, the surface of the sun will come probably out as far as the Earth, the 93 million miles, the one astronomical unit. But before that happens, the shock wave of the initial explosion of the sun consuming its final fuel in one orgy of brilliancy will destroy the Earth and turn it to dust. It is possible that Neptune or its moons might survive, but not much more. The solar system as we know it will be destroyed when the sun goes nova, which is one of countless reasons we human beings, if we want to have a future long term, should go into space. Eventually, that will happen, we think. But that nearby star's death causes a shock wave that moves through interstellar space. And that shock wave encounters a local dust cloud. And in that local dust cloud, the shock wave causes compression. Matter begins to clump. And our own Earth is born about 5 billion years ago. Thank you. Come again.